Okay, let's look at capacitors. So I can have conductors. So I have a pair of conductors, and I know that they will have a well-defined potential difference because each one in itself is an equal potential area. So what I've drawn is two potentials. One has a minus charge, one has a plus charge. You can even choose it such that there's an E field between them and around them, so that the potential is given by the integration between the negative charge and the positive side, the electric field dotted into the L vector. But Gauss's law tells us that the electric field is proportional to Q. Electric field is proportional to the charge. If I increase the charge, I increase the electric field. So if I double Q, Q. If I double Q, also double E. So that also means that the potential difference is going to be proportionate to the Q. The capacitance, which is the letter C, is equal to Q over delta V. Capacitance is a constant of proportionality for Q in V. That's how I relate the two, is through capacitance. Capacitance is going to be a purely geometrical quantity. Meaning it's going to depend on the object, it's going to depend on the size, the separation, the configuration, and the shape of the object or of the capacitor, but it's not going to depend on Q or the potential. Okay, it's a geometrical quantity. And what we'll find is that some of these situations are going to be easy to calculate if I know the electric field. Also, the SI units for capacitance is going to be farads. Farads is a really large unit, so we usually talk about microfarads or picofarads. Capacitance is going to be intrinsically positive, so it's always going to be a positive value. Okay, let's look at an example. If I have two parallel plates, one with a plus charge on it, one with a minus charge on it, I know that the electric field is going to be in between these two plates. Okay. And in between these two parallel plates, the E field is going to be equal to sigma over epsilon. Outside of here, E is going to be equal to 0. So my potential is going to be related to the negative of the electric field, which is going to be equal to plus sigma over epsilon naught times L. Where sigma is simply Q over A, charge per area. So the potential difference is going to be Q over A times L over epsilon for my two parallel plates. So what is the capacitance? The capacitance is going to be equal to Q over delta V. So plugging in my value for delta V, what I come up with is epsilon A, or the area times epsilon divided by L, which is Okay, let's look at another example. If I have two concentric circles, the inside circle has a charge of plus Q, which then gives me a charge of minus Q on the inner ring. The radius of the inner one is A, the radius of the outer one to the outside wall is B. Here the electric field is going to be 1 over 4 pi epsilon naught Q over R squared. That gives me a potential, again, it's going to be equal to the minus of this integral going from A to B. So my potential is going to be equal to this. And the capacitance is going to be equal to 4 pi epsilon times the quantity 1 over A minus 1 over B. Now, if B goes to infinity, right, then my capacitance becomes 4 pi epsilon naught times A if B goes to infinity. We can also talk about energy being stored in capacitors. And we could compute this, and it'd be equal to epsilon naught over 2 over the electric field squared over B. Okay. But you can also ask how much external work is needed to charge up this capacitor to Q. So if I have a capacitor and I want to charge it to Q, the question is how much work is needed to do this. Remember, I'm going to have to bring the charge over to the capacitor. So each dq that gets moved takes work. So dw, which is the work to move dq, is going to be equal to dq times the potential. But we've defined the potential. We could define the potential as Q over C, where C again is the capacitor. And it's going to depend on Q, which we've built up so far. So Q is going to be the charge that's already there on this capacitor. So the total work done. Okay, so again, work is going to be, we defined work earlier as potential times dq, and I'm integrating from 0 to q. It's going to be equal to 1/2 q squared over c. C again is capacitance, which can be written as 1/2 c v squared. So our sphere has stored energy, and the stored energy is going to be equal to 1/2 q squared over 4 pi epsilon naught a. Remember, the 4 pi epsilon naught a was the capacitance we calculated for our sphere when the second radius went to infinity. Okay, these are our short notes on capacitance and energy stored in the capacitors. So what I would like you to do is to try problem 2.43 in the new book and 2.39 in the old book, and we'll begin with these on Friday.